In this second lecture on the PFM, we are going to explore the contact mechanics and the resolution theory in PFM. In other words, we are going to explore where does the PFM signal come from and with which spatial resolution can we hope to observe the nanoscale details in ferroelectrics and other materials. To start, let's look at the philosophy of the scanning probe microscopy techniques, or in other words, the basic nature of the signal formation. So one broad class of the scanning probe microscopy techniques is based on the application of the bias to the probe and the detection of the current. So this is an example of techniques such as scanning tunneling microscopy, where this measured current is used for feedback, or conductive atomic force microscopy, when the current is measured as the function of position on the sample surface to give the information on local conductivity. And of course, the STM and conductive AFM are used for rather spectacular applications, including the atomically resolved imaging, spin polarized imaging, vibrational spectroscopy, and so on. The second broad class of scanning probe microscopy techniques is based on the force detection. So in this case, we apply force and we measure the mechanical displacement. So this is the example of atomic force microscopy, acoustic force microscopy. It's the basis for adhesion, elasticity measurements, and in fact, techniques such as magnetic force microscopy also rely on the mechanical detection. In comparison, PFM is based on the approach when we apply the bias to the probe and we measure the probe displacements. And this is the basis for electromechanical techniques, which can be used for measuring polar materials, biosystems, probing local bias-induced transitions, in other words, ferroelectric switching, or electrochemical reactions, or local spectroscopy. So, to remind you, the general principle of PFM is illustrated in this slide. We have this typical cantilever with the tip on end of it. The tip is brought in contact with the surface and we apply electrical bias to the probe. Due to the mismatch of the dielectric constant between the ambient and the material, the electric field is concentrated inside the material on the length scale of the contact radius. And if the material is piezoelectric, the piezoelectric coupling will result in the surface deformation in vertical direction and then cantilever deflection, or it will result in the shear of the surface in the lateral direction and the twist of the cantilever. So the former is measured as the vertical PFM signal, and the latter is measured as the lateral PFM signal. In general, in the most simple implementation of PFM, we apply the simple periodic bias to the probe, and we measure the amplitude and phase of the cantilever deflection due to the piezoelectric effect. Since PFM is pretty much the only technique that allows us to probe electromechanical coupling on the nanometer scale, we can write down that PFM is equal to nanoelectromechanics. The question, of course, becomes, what does the PFM measure? So what is the relationship between the material properties and the measured PFM signal? Currently, there are two primary implementations for PFM. One is based on the capacitor detection, when we have the top and bottom electrode. The material forms the planar capacitor, and the PFM tip is used only as the mechanical sensor that detects the displacement of the material induced by the uniform field acting within this capacitor. There are both pros and cons for this type of measurements. The pro in this case is that the electric field is uniform inside the material, which basically means that the signal is easy to interpret. Second pro is that the tip quality really does not matter, so all we need from the tip is detection of the surface displacement. The con is that the resolution is low because it's limited now by the electrode, and the classical electrical writing is impossible, even though it is possible to write in some cases using the pressure induced by the tip. So in this case, interpretation of the PFM signal is relatively straightforward. So imagine that we deal with a tetragonal ferroelectric material with the tetragonal axis oriented upward. In this case, in the laboratory coordinate system, the matrix of the piezoelectric constants can be depicted like this. So here, D33 is the vertical signal, D31 is shear components, and D15 are also shear components. If the material coordinate system and the laboratory coordinate system coincide, the PFM signal would be exactly D33, the lateral PFM signal in x direction and lateral signal in y direction would be the this coefficients of the tetragonal of the piezoelectric tensor. If we rotate the material by 90 degrees, the values of the piezoelectric tensor in the laboratory coordinate systems are going to shift like this, and our vertical PFM signal will become 0 as expected, and the lateral PFM signal would be the D15 of the material. So always need to look at the matrix of the piezoelectric coefficients in the laboratory coordinate system, meaning in the coordinate system related to the PFM. What happens if we go from the top electrode to the tip electrode? In this case, the bias is applied between the tip and the bottom electrode. So in this case, the resolution is higher, and we can write, meaning switch ferroelectric polarization by the tip. But in this case, the imaging becomes very sensitive to the tip surface contact, and it becomes difficult to interpret. So in this case, we need to differentiate different components of the PFM contrast. So we know that in the piezoelectric material, the electrical and mechanical phenomena are coupled, meaning that typically if we apply load, we create strain inside the material, so this is just a mechanical response. When we apply bias, we create a potential. But in the PFM, if we apply load, we also affect the potential, and if we apply bias, we create strain. So there are these cross-coupling terms. So if we want to understand the PFM contrast, we need to understand this voltage-dependent tip surface contact mechanics. We also need to understand the cantilever dynamics, which is the detection mechanism by the scanning probe microscope. And we also need to understand the field structure inside the material, because this is what determines the resolution, this is what defines the hysteresis measurements, and this is what controls the switching phenomena. So let's start with the tip surface contact mechanics. So what happens if we have the tip? We apply the load and the bias, and we want to find the strain and potential inside the material. So in the local case, the exact solution is available only for the transversal isotropic materials, and as a good zero-order approximation, we conjecture that vertical PFM signal is the D33, X LPFM signal is D34, and Y LPFM is the D35. So this is a zero-order approximation, and in the rest of this presentation, I will illustrate how we can derive exact and approximate solutions for more complex. Secondly, contribution to the contrast in the real world is the contribution from the local and distributed electrostatic forces. So in this case, the electromechanical signal originates in the tip surface junction. However, in this tip surface junction, we also have the local electrostatic force. Basically, this is the force between the tip and the surface due to just electrostatic interaction, just capacitive forces, which also results in the tip indentation in the surface. And the third contribution is the non-local forces between the cantilever and the surface. So these forces result in the cantilever bending, but as we have seen, this cantilever bending is also detected as the vertical displacement of the probe. In fact, if we quantify these different interactions and their magnitude as the function of tip radius and the indentation force, we can derive this reasonably complex map that shows what regimes of interactions are possible. So, for example, in the regime when the tip radius is relatively large, but the indentation force is small, our interaction is going to be controlled by the pure electrostatics. If our indentation force is large and the tips are sharp, then our interactions are going to be limited by the plastic deformation of the surface and the tip, so we exceed the mechanical stability of the material. If our tip is very sharp, but indentation forces are intermediate, our interactions would be non-local, so they will be controlled by the cantilever. If we are in the regime where the tip radius is intermediate and indentation forces are intermediate, we would be controlled by the local electrostatic interactions. And finally, only in the regimes when the tip is relatively blunt, but the indentation forces are pretty large, our interactions are going to be controlled by the electromechanical signal. So this is what we call the strong indentation regime. Second component is that we need to consider the lateral displacement. So in this case, we have to take into account the vertical surface response, longitudinal response, sort of along the cantilever axis, the torsional response, electrostatic forces, and distributed electrostatic forces. So these are the components of the PFM signal, and throughout this lecture, we are going to go through them one by one, starting from the tip surface contact mechanics. So obviously the question is, can you read about this in more detail? And these are the references that talk about the basic image mechanism of the PFM on the ferroelectric surfaces and quantification of the PFM interaction. So let's start with the voltage-dependent contact mechanics. So at this point, we are not interested in the cantilever, we are not interested in the detection, we just want to understand what happens at the junction between the tip and the surface. And the convenient way to explore this interaction is through the analog of the force distance curve. So in classical scanning probe microscopy, it is common to represent the different regimes between the tip surface interaction between the tip surface force. So if we are far from the surface, then we are in the attractive regime on the van der Waals forces. If we are in contact, this is the regime of the acoustic microscopy or contact AFM. If we are performing something like tapping mode AFM, our tip moves along this force distance curve. But of course, the force distance curve doesn't include bias effect. And if we add them, then we generalize from the force distance curve to the force distance and bias surface. And we can understand the electromechanical scanning probe microscopy techniques based on the shape of the surfaces. For example, if we are not in contact with the surface, then the shape of the surface is given by the simply capacitive forces. So this is parabola. So techniques such as Kelvin probe microscopy measure the force as a function of bias. Techniques such as electrostatic force microscopy measure the signal as a function of distance. While we are in contact with the surface, then techniques such as atomic force acoustic microscopy essentially measure the stiffness, or in other words, the derivative of the force distance curve versus distance. And of course, this derivative can be bias dependent. So depending on the tip bias, surface can change mechanical stiffness. PFM measures the derivative in the direction of the bias. So in other words, surface displacement versus the bias. There are more complex techniques such as ultrasonic force microscopy or heterodyne electrostatic force microscopies that will measure the signal proportional to the second derivative of this force distance bias surface. So one of the important things about the PFM, kind of continuing the slide of the philosophy of scanning probe microscopy techniques, is that the nature of the signal very much depends on what we apply and what we measure, and that determines both the tensorial nature of the signal and it determines the scaling with the contact radius. So for example, in techniques such as STM or conductive AFM, we apply bias and measure current and the signal is scalar. Also, this signal strongly depends on the contact radius. It's either the first or second power of the contact radius between the tip and the surface. In the techniques such as AFM or acoustic force microscopy, the signal is actually a second-rank tensor, and unfortunately only two elements of this tensor are measurable directly. And also the contact stiffness scales as the first area of the contact radius, which means that AFM signal is very strongly dependent on the topography. Interestingly enough, for the electromechanical techniques, the signal is in the zero approximation independent on the contact radius. So this can be derived simply from the dimensionality arguments. So there are two conclusions out of it. First of all, PFM is complementary to STM and AFM in terms of imaging mechanism. And secondly, PFM can be quantitative. So question is, of course, quantitative is great, but what is that we measure? It turns out that for the transversely isotropic material, which is the highest symmetry possible for ferroelectric material, we can derive the analytical theory for the voltage-dependent contact mechanics. So the examples of the transversely isotropic materials is something like barium titanate or poled polymers or poled lithium niobate. So in this material we don't have any lateral response, we have only a vertical PFM signal. So this solution would be limited. However, it would be also a good starting point for more complex systems. So having the exact solution, we can learn how to derive approximate solution. So in this case, the contact electromechanics is basically the extension of the classical Hertz model. And it took quite a while to develop. So Hertz model for the spherical indentation of the isotropic material was developed in the 1872, so more than 150 years ago. In 1945, Snedden have extended this theory for the arbitrary indenter shape, so it no longer has to be a sphere, it can be something more complicated. And in 92, barely 30 years ago, Hansen have developed this theory for the transversely isotropic material. And in 2002, about 15 years ago, Karapetyan and Kachanov have extended this theory further towards the piezoelectric material. So what they did was basically to derive the rigorous solution for spherical indentation for piezoelectric material and analytical function and summarize this in the form of stiffness relations. So stiffness relations define the relationship between the load on the indenter, or if you will, the force acting on the tip, P, and the contact radius and the indenter radius, so A and R. And the second term here is the additional contribution to the load as a function of the tip potential. Similarly, they derive the relationship between charge and the indentation force and the indentation and the indenter bias. So in this representation, the parameter C1 is the elastic stiffness. This is the equivalent of the indentation modulus. C4 is the indentation dielectric constant. So this is the equivalent of the dielectric constant for the planar arrangement. And C3 is the indentation piezoelectric coefficient. So one important discovery was that this is the same constant C3, which is equal both for load potential and charge displacement terms. Later, in another 3 or 4 years, this contact mechanic models was generalized for arbitrary indenter shape, so for planar indenter, for spherical indenter, and for conical indenter. And the structure of this stiffness relationship between the load and charge on the indenter and the indentation depth and the indenter potential is basically the same. So compare these two equations to the equations for the uniform field. So in the uniform field we have the same constant d33 that defines the relationship between displacement and voltage and charge and force, so the converse and direct piezo effect. And for the contact mechanics we have the same constant C3 that defines the coupling between the load and potential and charge and displacement. Now, what are the consequences of this contact mechanic model? So the first very important consequence is that in any scanning probe or indentation experiment, we can determine only indentation moduli, C1, C3, C4. We cannot determine the individual elements of the elastic, piezoelectric or dielectric tensors. So this is just an issue of observability, same as in the contact mechanics, where we can determine the indentation stiffness, but we cannot determine the individual elements of the stiffness tensor. Secondly, in contact problem, the indenter shape function on material properties are decoupled, which basically means that the indenter can be calibrated. What's also important is that if we measure electromechanical coupling, we actually don't even have to calibrate the indenter, but we'll get to this in a minute. Experimentally, techniques such as PFM measure the ratio of C3 to C1, for example, atomic force acoustic microscopy measures C1. Theoretically, dielectric measurements would be able to measure C4, the effective dielectric constant, but practically, since it's extremely small, it cannot be measured directly. We can measure only the derivative of it. So wonderful. We noticed that this PFM experiment can access this parameter C1, C3, C4. However, these are really complicated functions of the material properties. So the question is, can we somehow simplify those? It turns out that what we can do is to analyze the sensitivity of these parameters towards specific materials properties. For example, we define the sensitivity as the logarithmic derivative of the indentation modulus versus the material parameter. And we look at the, for example, dependence on the indentation modulus on the elastic stiffnesses. And you can see that this dependence is pretty complicated. At the same time, if we look at the dependence of the piezoelectric stiffness on the materials parameters, we can see that rather remarkably, this piezoelectric stiffness is almost independent on the elastic properties of material. So even though this parameter C3 is a very complex function of all material properties, practically the dependence on the elastic part is actually very weak. However, it is very strongly dependent on the D33 and the D15, and when we say that in the zero approximation our piezoelectric stiffness is actually D33, that's exactly correct, so the numerical analysis confirms it. And what's interesting is that this piezoelectric stiffness is also determined by the epsilon 11 and epsilon 33, the dielectric properties of the material. And once we go from the exact solution to the approximate solution, these dependencies come into play very significantly. So we'll see that this sensitivity analysis actually suggests how to look for the approximate solution for the PFM. Another way we can look into this data is simply plot the expected piezoelectric response in PFM versus D33 for the material, for a range of the materials. And you can see that, interestingly enough, for a rather broad range of the ferroelectric materials, the expected piezoelectric response in PFM, so the solution of the exact equation, and the D33 fall on pretty much the same curve. So when we say that in the zero-order approximation PFM measures D33, we actually have pretty good reasons for saying that. In comparison, for if it were possible to measure the dielectric properties, that would be almost exactly geometric average of epsilon 11 and epsilon 33 for the material. So in other words, we don't know the indenture charge, but we can obtain it from the simple theory from the dielectric. What are the implications for the electromechanical SPM? So in PFM, we measure this effective piezoelectric constant D effective, which is derivative of the tip displacement with respect to the tip bias, which is C3 over C1. In comparison, in techniques such as atomic force acoustic microscopy, we measure the mechanical stiffness of the tip surface junction, which actually depends on the indentation depth and the tip shape. So as a result, we have good news and bad news. The good news is that the PFM signal is actually independent on the tip geometry and topography. So PFM signal is fundamentally quantitative. That's great. The negative thing is that we cannot use the resonant enhancement in PFM directly. And the reason for that is that if our resonant frequency of the cantilever shifts, the signal as measured by the cantilever also shifts. So the surface oscillates with the same magnitude, but the cantilever displacement is determined by this transfer function, which is dependent on whether the material is soft or hard. And throughout this lecture and next lecture, we are going to look into this in more detail. So again, there are several references. So the theory of the electromechanical signal in the PFM is discussed in the following set of papers, so which explore the nanoelectromechanics of PFM and explore the reciprocity between the forward and converse PFM effect. In this publication, the general solutions for arbitrary cantilever shape were determined, and in this publication, so it took almost 10 years, the solution for the point force and point charge for the arbitrary three-dimensional solid were derived. Also, over the last decade, the effects of the friction and the bonding between the tip and the surface were discussed, and the implications for indentation and the SPM were discussed in the following contribution. Now, what about approximate theory for PFM? So the rigorous solution that we discussed above is very limited. So first of all, it ignores the fields outside of the contact area. So this is a classical approximation in the contact mechanics. Secondly, it is limited to the transversely isotropic material, so meaning that we don't have any lateral PFM, and practically it doesn't apply to any material other than 100 surfaces of the perovskites. It also cannot be used to describe the PFM signal in thin films, nanoparticle, domain walls, cylindrical domains, and so on and so forth. So in other words, it's an exact solution, but this is the solution which is useful only to calibrate our measurements, but it doesn't allow us to describe anything interesting. So we need the approximate solutions. How are we going to find it? And it turns out that the sensitivity analysis of the exact solution suggests that the approximate solution can be looked for in the form of the linear combination of the piezoelectric constants multiplied by the function of the ratio of the dielectric constants, so the dielectric anisotropy. And the reason why we know that is because we can see it in the sensitivity analysis. So it shows us that our piezoelectric stiffness is almost independent on the elastic properties of the material. It is strongly dependent on the piezoelectric constant, and it depends on the ratio of the epsilon 11 and epsilon 33, simply because the logarithmic derivative is equal and has opposite side. We can also speculate that for the general anisotropy, we can generalize and look for the PFM signal, both for vertical and lateral PFM, as the linear combination of piezoelectric tensor elements multiplied by this function of the ratio of epsilon 1 and epsilon 33. So how are we going to find these expansions? And we are going to do it through so-called decoupled approximation. suggested by Muna Saldana and Gerald Schneider about 15 years ago. So in this decoupled approximation, we first calculate the electric field for rigid dielectric, so assuming that the piezoelectric constants are small. Then we calculate the stress field using the piezoelectric constitutive equation. So we turn on the piezoelectric coupling and calculate the stress fields. And then we calculate the displacement fields using the Green function for the non-piezoelectric solid. So in other words, first we assume that the piezoelectricity affects the dielectric properties only weakly. Then we say that piezoelectricity in fact creates stress. And secondly, we say that the piezoelectricity affects the mechanical properties only weakly and calculate the displacements. So we get a nice expansion for the surface displacements. So here G is the Green's function for the material, E is the electric field, and C is the elastic constants, and D is piezoelectric constant. So the nice features of this decoupled Green function method is that it can take into account any field structure. So we can solve electrostatic problem even if it is pretty complex. We can play with the material symmetries. For example, we can use the exact symmetries for dielectric, piezoelectric, and elastic tensor, or we can use approximate ones. It can be naturally used to describe microstructural elements such as variation in elastic properties, domain walls, and so on and so forth. And we can further simplify it by assuming that special material symmetries for elastic and mechanical properties. So, interestingly enough, we can even estimate how precise is this decoupled approximation. So we can get the error for the estimate as this constant Kij, which is the square of a piezoelectric constant divided by product of the stiffness and dielectric constant. And it turns out that for materials such as barium titanate or PZT, the error is somewhere between 10 and 30%. For weakly piezoelectric material, the error is of the order of the 1%, which basically means that this theory is not exactly precise. We still have 10-20% error, but at the same time, it is actually pretty good for such a complex. So this is how we proceed. So the first step is to calculate the electric field inside the material. And in general, we can do it using the either image charge series or the multipole expansion, or we can just solve the Laplace's equation for the material. So in general case, we can show that the field created inside the material can be obtained in this following functional form. So this is just a standard electrostatics. For the transversely isotropic material, the solution becomes really simple. So in this case, if we represent the tip by the point charge, the field inside the material can be represented as the following functional form. Our second step is to analyze the signal and try to understand what type of approximations we can introduce. And it's very instructive to look at the dielectric surface, meaning the orientational dependence of the dielectric response, piezoelectric surface, and the elastic surface of the material. You can for barium titanate and for lithium niobate. And you can see that elastic properties of these materials are of course orientation dependent, but this dependence is relatively weak. In comparison, piezoelectric surfaces are extremely strongly orientation dependent because they change sign from positive to negative. Dielectric properties are also relatively weakly orientation dependent. Therefore, one step that we are going to do is we are going to approximate the elastic properties as purely isotropic. And if we do that, we can actually evaluate these complex integrals, including the Green's functions, analytically, and simply derive that the piezoelectric signal would be proportional to the charge magnitude multiplied by the following function of the dij's. So if we go through the algebra, we basically obtain that piezo response is equal to product of the piezoelectric constant times the function of gamma, and gamma is the dielectric constant. Notice that this simplified formula that is obtained in the decoupled approximation is exactly what we speculated based on the sensitivity analysis. We also derived the response theorem that says that for transversely isotropic piezoelectric solid in the isotropic elastic approximation and arbitrary point charge distribution in the tip, so not necessarily constrained to a single line, the vertical surface displacement is simply proportional to the surface potential induced by the tip and the point of contact. So in other words, we get the full description of the PFM. For an isotropic material, we can go through the similar type of derivation, and we get the second response theorem that for an isotropic piezoelectric solid, in the limit of dielectric and elastic isotropy, the vertical and lateral PFM signals are proportional to the potential on the surface induced by the tip if the tip charges and the point of contact are located in the same line along the surface normal. Of course, using this mathematical theory, we can develop the response theory for the non-standard probes. For example, for the strip line probe, quadrupolar rotating probes, the shielded probes. And the relevant references would be given on these slides. So the decoupled approximations is introduced by the paper by Felton, Schneider, and Muniz-Saldana. The PFM signal formation mechanism is described in these two contributions. And the applications for the films, capacitors, and other systems is given in those papers. Now, let's transition to the resolution theory. So, how high a spatial resolution can PFM give us? And of course, here the first question is, what is resolution? In optics, the classical definition of resolution is based on so-called Rayleigh criterion, which basically defines at which distance between the 2 point scatterers they can still be distinguished. So if they're distinguished, the profile goes like this. If they're almost distinguished, the profile is still barely visible. And finally, if they're too close, below the resolution, we see only one object rather than two objects. So clearly, this is a very simple definition, and the more sophisticated approach is so-called the linear resolution theory. So basically, the linear resolution theory says that the ideal image can be represented by some spatially dependent field I0. The experimental image is the convolution of the ideal image with the resolution function. So the same type of relationship can be established in the Fourier space, where the ideal image in the Fourier space and the experimental image in the Fourier space are related by the multiplication by the object transfer function. So the question is, can we establish the resolution and information limits in the PFM, and how this resolution and information limits depend on the tip geometry and material properties? Can we develop the pathway to calibrate the tip geometry? Can we interpret the imaging and spectroscopy data in terms of the intrinsic material parameters? So what can we learn about the material? And can we reconstruct the ideal image from the experimental data? So let's look at this resolution and information transfer behavior in a little bit more detail. So how does the transfer function look like in the techniques such as transmission electron microscopy or scanning transmission electron microscopy? So in TM, the resolution function is remarkably complex, kind of goes like this. And generally, the Scherzer resolution is defined as the first zero of the transfer function, and information limit is defined as the value of the inverse vector where we no longer obtain the information about the material. In scanning transmission electron microscopy, the resolution function looks like this. So here we have the Scherzer resolution limit, and here we have the information limit. So in scanning probe microscopy, typically the transfer function looks like this. And therefore, we define the resolution using the analogy with the Rayleigh criterion when the transfer function becomes 0.73 of the value at 0. The information limit, however, is determined as the crossover between the transfer function and the noise, normalized noise in the system. And this is how it looks in the for real example. So imagine that the ideal image looks like this. We just have a grating of the positive and negative domains. The good image is the convolution between the transfer function and the ideal image. So it still looks like a grating, but it's now smooth because we have some finite resolution effects. So this smoothing defines the boundary of the resolution. So if we go in this region, we still see the periodic features, but their magnitude is no longer equal to the ideal image. Now, if we add the noise to the system, we can still see features, but they're corrupted by the noise. So once we stop seeing the features, when the noise becomes more visible than the features, this means that we're in this region, so we move further than the information limit. How can we develop the resolution theory in PFM? So the first step is, of course, to prove whether the image formation mechanism is linear in the first place, because, for example, the topographic imaging in PFM, in AFM, is non-linear. So it turns out that once we develop the resolution theory and the decoupled theory, the PFM image already can be represented as the convolution between the ideal image, meaning the distribution of dij's, and the transfer function. And this transfer function can be obtained in the analytical form from the decoupled theory. It turns out that we can evaluate it in the point charge model or in the sphere plane model, and it has the opposite or obvious physical sense. So it depends on the tip radius and on the dielectric anisotropy of the material. This in turn allows us to calculate the domain wall profile. So domain wall profile is a natural observable in PFM. We know that in most ferroelectric materials, the domain walls are atomically sharp, which basically means that the observation of the domain wall in PFM and experiment tells us what is the size of the tip. So rather than probing the wall with the tip, we actually probe the tip with the wall. And we can calculate the behavior of the piezoelectric piezoelectric signal across the domain wall for different material classes. What's also interesting is that we can measure the strength of the lateral PFM signal across the domain wall. So we can predict that for ferroelectric domain wall, 180-degree ferroelectric domain wall in barium titanate, we expect to see the non-zero lateral signal. So it's easy to imagine how the combination of the vertical response in one direction in positive domain and downward direction in the negative domain also creates the in-plane shift across the wall. As you can see that depending on the dielectric and mechanical properties of the materials, we expect the different thickness of the domain wall as measured by the PFM. And generally it is kind of comparable to the tip. As I said, this allows us to calibrate the tip parameters, and we do that by taking the experimental domain wall and then using this formula to fit it by finding the equivalent magnitude and position of the charges. That's remarkably interesting because for most materials, it turns out that the single charge provides remarkably good description of the tip behavior, but in virtually all cases, the characteristic size of the tip or separation between the charge and the surface is of the order of hundreds of nanometers. So it's surprisingly large. The only exception is the PZT in liquid environment, where the wall width is actually very small and the equivalent charge surface separation is about 10. The question is, why is the tip so large? The answer is we don't know exactly, but one thing we do know is that once we do the measurements in air, there is typically a water meniscus forming between the tip and the surface. And this meniscus can be actually pretty large, of the order of hundreds of nanometers. So we can speculate that part of the reason why PFM signal has a relatively low resolution is that the presence of this water meniscus strongly affects our imaging mechanism. And this is something that we really need to take into account and try to do the measurements in the controlled environment or in vacuum. We of course can extend the same approach towards imaging the periodic structures. For example, if our domain structure is the grating of domains up and down, this is our ideal image. This is just Fourier expansion for this type of periodic function. We can get the expansion for the real image, and we can show that for low resolution only the senior Fourier component survives, and this is how its intensity is going to depend on the relative domain size versus the tip size for different. We can also use the same approach to analyze the signal from the cylindrical domains, and this is really important for analysis of the PFM spectroscopy experiment when we use the PFM tip to switch polarization and measure the signal in terms of the applied bias. Again, in this case, we can use decoupled approximation. We find a solution for transversely isotropic ferroelectric, and we can use the Pade approximation. So this is essentially the expansion in the polynomials to get the approximate formula that gives us the measured piezoelectric signal from the cylindrical domain. So in this case, the components is basically the relationship between the tip size and the radius of the domains. And we can easily analyze how the resolution is going to affect our imaging. So for low resolutions, the domain are difficult to distinguish. The signal in between the domain will go up, but domains are always visible as long as our signal strength is above. Next question is, what is the smallest feature that we can determine but not quantify? In other words, what is the information limit in the PFM? So in this case, PFM information limit is the non-universal function of the system, so it's determined by the system noise. But again, we can analyze it, and depending on the specific material and the system conditions, we can determine what is the minimal feature size in terms of tip radius that we can determine in different materials. Question is, can we measure these parameters experimentally? So in this case, we can show that the Rayleigh resolution, so the classical resolution, is simply the width of the domain wall. But the information limit can be determined as the width of the domain wall in the phase image. So the derivation is relatively straightforward, but here just take it for granted. Which basically means that we can experimentally measure the resolution if we create a pattern like this. So this is our ideal pattern. This is the voltage we use to write the ferroelectric domains, and this is its Fourier transform. This is the image that we obtain after scanning this, and we do the Fourier transform, and we can see what is the minimal feature size that is still detectable in this image. So we can explore how this feature size depends on the setting on our lock amplifier. For example, if we start to increase the lock and amplifier time constant, our image start to change from pretty well determined, but we already see the noise band in corresponding to the smearing in this direction. So if we increase the time constant, you can see that the image becomes more and more smeared out, and you can see how our resolution changes. So we stop seeing the small features, we start to see only relatively big features in the image. We can explore this lock-in effect on resolution through the wave vector depends on peak intensity. So it goes like this. For small lock-in time constant, our signal is not optimal, so we are letting too much noise through the system. Once we are at the optimal time constant for the lock-in, we have the maximal peak intensity, so this is the optimal imaging condition. And then once we start to go to the large time constant, the noise is decreased, but now our image is smeared, so our peak intensity goes down. So we can establish the optimal observation conditions for our. And we can even calibrate the transfer function if we create the variable mesh standard. So here the domains change in both x and y direction. We can write the domain pattern like this. We can read it using the PFM, and we can take this ratio of the Fourier components in order to reconstruct the transfer function. And then we can use the regularized reconstruction methods in order to go from the relatively weak experimental signal to a reconstructed signal, which becomes as a result much sharper. So this is the example of how the knowledge of the imaging system can actually improve our data. Again, this lecture is summarized in the following publications. So this publication summarizes the concept of resolution, information limit, and contrast transfer. These two publications define the analytical theory for resolution theory and for walls and domains and spectroscopy, and this one for films. These several papers summarize the studies of the calibration for the PFM, and also some of these contributions are summarized in the following 3 books. Thank you.